Welcome to Calculus 1. Today we're going to talk about what we so-called the implicit differentiation. Alright. Most of the functions so far that we're seeing in this course has been expressed in explicit form, where the variable y is explicitly written as a function of x, just like y equal to x squared plus 1. Okay, we see a lot of y equal or f of x equal. That's the way how we've been written so far. Now, implicit functions are implied by an equation, okay, such as x to the third plus 2y to the fourth minus 4y equal to 7. So, equation like this cannot be written as y equal. Okay, it cannot be expressed in explicit form. So, if we want to take a derivative, okay, of y in respect of x, we have to use what we so-called the implicit differentiation. So, implicit differentiation is when differentiating terms involving x alone. Okay, we will do so. We will differentiate as usual. Now, when we have to differentiate terms involving with y, we will actually use what we so-called we will actually use the chain rule that we talked about before. So this is how it goes. For example, okay, the issue is if I want to take a derivative in respect of x, my y to the 4 has no x in it. Okay, so I'm going to treat this using a chain rule. I'm going to treat this y to the 4. I'm looking at it as like a u to the 4 power. So as you when we use the power rule, okay, we're using a chain rule, that will be derivative of the outside. Derivative of the outside, which is using the power rule, that will be 4. Okay, derivative of the outside of the inside. So that would be a 3 right there. The exponent drop out 1 times the derivative of the inside. Okay. So since I cannot take a derivative of the inside, we will just write it as y prime. Or in our case, I'm looking at it as a u. Okay. Looking at it as a chain rule. So if you look at what's in the inside, okay, the inside will just be u prime. Okay, this is the idea of differentiating with only respect to x. When my function does not, when my term does not have x in it, we will actually use a chain rule. Okay, so I'm basically trying to use the power rule, which is n times u to the n minus 1 times u prime. Okay, so for my answer, derivative of the outside, that would be 4 of the inside, and then exponent drop by 1 times the derivative of the inside. Since I cannot take a derivative of the inside because I need to do it in respect to x, the variable doesn't match here, so that would just be y prime or dy dx. Okay. In a way, I remember my college professor told me that when you write dy dx here, that means you're actually trying to take a derivative of the y in respect to x, even though you can't really do it because there's no x in your original function. And that's the way I'm thinking about it too. But I'm also see it as using chain rule to help me to write this answer out. So that's the answer. So the reason, a lot of times this is getting a little bit confusing. Why is there a dy dx over there, as part of my answer? And if you really think about it, besides using a chain rule, you are taking a derivative of y in respect to x the whole time with the y to the 4, even though there's no x there. So you got to tell the reader, okay, what you were trying to do here with this y to the 4. Alright, addition sign, allow me to separate. So I'm going to rewrite this problem as derivative in respect of x of 2x squared plus excuse me, derivative of 3y in respect of x. Alright, the sum and difference of differentiation still apply here. So now the variable match. Okay, so I will just take derivative normally. So derivative of 2x squared, that will give me 4x. Alright, plus, take out the constant, so derivative of the y, that will just be 1, okay, times dy dx. Because I'm taking a derivative of x, okay, I'm taking derivative of y in respect to x. So normally y is y to the first power. So if I'm using a chain rule, derivative outside is 1, and the exponent subtract 1 of the inside, which is still, okay, which is still y. Okay, derivative of the outside, that means bring the exponent down. Of the inside, still y, but my exponent now becomes 0. So y to 0 is 1. 1 times 1 is 1 times the constant. But we got to make sure we write dy dx. Alright, and that's it. That's the answer. Okay, implicit differentiation. Alright, let's use some product rule here. Okay. So this is going to be derivative of the first. So I'm going to write it like this. I'm going to take a derivative of x squared derivative of the first times times the second plus the derivative in respect to x, derivative of the second times the first, which is x squared. Okay, using product rule. Alright, let's simplify this. Derivative of x squared in respect to x will differentiate normally, so that will give me 2x times y squared plus derivative of y squared in respect to x, so derivative outside, okay, of the inside, my exponent goes down by 1, times dy dx times x squared. So if I simplify this a little bit, this answer is nothing but 2xy squared plus 2x squared y dy dx. Alright, so let's take a look at some of the steps. Okay, some of the steps. So these three examples, I'm just trying to show you how we normally differentiate. Okay, with respect of y, we right now we'll view it as like a chain rule. Okay, derivative outside of the inside times derivative of the inside. So dy dx is derivative of the inside itself. Alright, some of the steps. So for this problem here on your handout, if I want to find the dy dx, we will differentiate both sides of the equal sign with respect to x first. Then we're going to move all the terms that have dy dx to one side and move all the other terms to another side. Factor out your dy dx and we will solve for it. So real simple, this is how it works. Okay, I got 1, 2, 3, 4, 5 terms here. Take a derivative of the whole left side and the whole right side. Alright, so using the sum and difference rule, So derivative of y to the 4 in respect to x. So that will give me 4y to the third. Okay, derivative of the outside of the inside times derivative of the inside, which is dy dx. Because in reality, we really cannot take a derivative of y to the 4 in respect to x because there's no x here. That's the reason why we view this as a chain rule. Plus, alright, derivative of y squared in respect to x, that will be derivative of the outside of the inside. Exponent go down 1 times derivative of the inside, which is dy dx, minus 5. So this is y to the first, derivative of the outside is 1 of the inside, just like earlier. Y to the first is basically derivative of the outside is 1 of the inside, and the exponent go down by 1, so that becomes 0. So that would just be 1, or just a 5 here, times derivative of the inside, which is dy dx. So this is going to be 5 times dy dx. Alright, minus derivative of x squared in respect to x. We will differentiate that normally, so that would just be 2x equal derivative of 4 is 0. Alright, so I'm going to move the negative 2x to the other side, and at the same time I'm going to factor out all these dy dx. So if I factor out the dy dx here on the left side, that will leave me with 4y to the third plus 2y minus 5 equal to positive 2x. Move over to the right side. Alright, so to get dy dx by itself, I will divide it by this big old thing on both sides. So my answer, dy dx, will just be 2x over this big old thing, 4y to the third, plus 2y minus 5. Now I can also using implicit differentiation to help me define the slope of a tangent line, okay, of different graphs, such as an ellipse, okay, at a particular point here. So here is an equation for an ellipse. You probably seen these equations in trigonometry class. In these problems, you cannot really write it as y equal. It's kind of difficult to write as a y equal. So, if I want to find the slope of a tangent line, okay, at this particular point, I can differentiate, okay, in respect to y, and then just do exactly the same thing as we done in the previous problem, where at the end I want dy dx to be by itself before I can evaluate, at this point to find my slopes. Alright, so take a derivative of x squared in respect to x. That will be normally just 2x plus derivative of 4y squared in respect to x. So that will be derivative of the outside, which I will move the 2, using the power rule, I'll move the 2 down. So 4 times 2 is 8. Alright, of the inside, derivative of the outside of the inside. Exponent go down by 1 times derivative of the inside, which is just to be dy dx, equal derivative of the 4 is 0. Alright, so I'm going to move the 2x over and divide both sides by 8y. So my dy dx is going to be negative 2x over 8y. That would be negative x over 4y. Alright, so at this point, okay, at this point, the slope of the tangent line at this point, that will be negative. I'm going to write it like this. My dy dx will equal to negative x is square root of 2 over 4 times y is negative 1 over square root of 2. Now let's evaluate at this point. So this is going to be negative square root of 2 over negative 4 over square root of 2. And I think my answer will be positive. So division of a fraction means times the reciprocal. So if we flip it, that will give me square root of 2 that was on top times reciprocal. The square root of 2 will flip to the top, still divided by 4. So square root of 2 times square root of 2 is 2 over 4, which will make a half. Alright, so the slope of the tangent line at this point is half. Let's look at an example for limit gate. Okay. So this one is a little bit more complicated. Alright, so I'm going to write like this. Okay, I'm going to write it out. So I'm going to take, same thing, I'm going to take a derivative in respect to x of this whole left side. And I'm going to take a derivative in respect to x of the right side. Okay, so I can put out this constant to the front. So this is going to be 3 times the derivative of the outside. This, I gotta use a chain rule here. Derivative of the outside of the inside. So that'll still be x squared plus y squared. Exponent is 1 now, go down by 1. Times derivative of the inside. The derivative of the inside. The first term is 2x, so that would just be, excuse me, for the x squared that would just be 2x. Plus, when I do the derivative of the inside here, for y squared, that would be 2 times y times dy dx. Okay, derivative of the outside of the inside y times derivative of the inside, which is dy dx, equal. Alright, I'm gonna put out my constant 100. Derivative of the first is 1 times the second plus the derivative of the second, which is 1 times dy dx. Times the first, which is x. Alright, let's simplify this real quick. This is a little bit tricky. Okay, 3 times 2 is 6. Rather than take the 6 times x squared plus y squared, rather than distribute the 6, I'm actually gonna take the 6 times the 2x, which will give me 12x, and that 12x will eventually still times this x squared plus y squared, plus this 6 times the 2y here gave me 12y, and that 12y again will times the same thing, so that will give me 12y times x squared y squared and of course my dy dx I'm gonna put at the end here. Alright. You will see why we do it like this just in a minute. Equal. This is just y. 100 times y is 100y. This is just x times dy dx. So 100 times x, that will be 100 x dy dx. Alright, so this term has dy dx in it. So is this term. So I will move the 100x over to the left side. At the same time, I'll move the 12x times to the other side. So that will give me 12y x squared plus y squared dy dx minus 100x dy dx equals the 100y minus 12x times x squared plus y squared. Alright, factor out the dy dx. Now it just leave me with this minus the 100x. So to get dy dx by itself, I will have to divide it. So my dy dx will end up 100y minus a 12x times x squared plus y squared divided by whatever coming from the other side, which is 12y times x squared plus y squared minus 100x. Alright, so this is my slope. So if I want to find a slope at 3, 1, I will plug in 3 for x and 1 for y. Okay, and if I do that, I will end up with 13 over 9. That's my slope of the tangent line. Okay, a little bit more writing here. Now I'm going to use the next example to kind of show you a very unique technique that we can use. Alright, find the second derivative, okay, implicitly. So I'm going to take the derivative in respect of x, but I'm going to do it twice. So check this one out. Alright, there's a cool technique in the middle of the problem here I'm going to show you. If I want to take derivative of x squared in respect to x, that would just be regularly 2x plus take a derivative of y squared in respect to x, that would just be the derivative of the outside of the inside times derivative of the inside. So that would be dy dx. Alright, derivative of 36 is 0. So move the 2x over and divide both sides by 2y. Get my dy dx by itself. That will just be negative x over y. Alright, so now I'm going to take another derivative for the second time. So that will be d squared y over dx squared. Okay, this is the way how we write it for the second derivative. So that will be negative derivative of the top times the bottom. So that would just be y minus the derivative of the bottom, which is 1, in dy dx, because I'm taking the derivative in respect to x, so for my y would just be dy dx times the top over the bottom squared. Alright, now what I got myself here okay, is negative y minus x times dy dx. Okay, but you see this is cool. The dy dx is already negative x over y, so what I can do is substitute negative x over y for my dy dx. So that will be negative y minus x, second term x will times the negative x over y. So I am substitute negative x over y for the dy dx, whole thing over y squared. Alright, if I continue to simplify, this is going to be negative y plus x squared over y squared. Alright, I'm going to multiply top and bottom by y over y, so I can get rid of this y right here. That'll give you negative. Okay, y times y is y squared plus y times this second term will just be x squared over y to the third. And this is real neat. What is y squared plus x squared? And I go back to the beginning of the problem. Y squared plus x squared is 36. So my answer will actually be negative 36 over y to the third. There you go. So a lot of substitution of the things that we already came up with. Okay, even go back to the original problem. Alright. Now, the last thing I want to show you in today's video is using logarithm, okay, to help us differentiating non-logarithm functions. Okay, sometimes this is actually pretty useful. Okay, so if I want to take a derivative of this function, I can actually take a derivative using the quotient rule here for the right hand side, the equal sign. Alright, but another technique, I just want to show you this technique, is actually using the properties of a logarithm. So what I'm going to do is take a natural log on both sides. Let me write it out so you can see why. If I take a natural log on both sides, it will look something like this. And as you can recall, one of the properties of natural log, or many properties of natural log, is saying that a natural log of a quotient will be the top, natural log of the top subtract the natural log of the bottom. So we can rewrite this whole problem as a natural log of y equal to, remember the exponent, go to the front, that will be 2 times natural log of x minus 2 minus the division means subtract. Square root is a half, so bring it up front of the natural log. So that'll be half times natural log of x squared plus 1. So we can basically rewrite this whole problem like this and differentiate, okay, accordingly. Alright, remember natural log, take a derivative of natural log is 1 over, okay, 1 over u times u prime. Alright, so that will be 1 over u, my u is like my y, times u prime, which is just y prime, or dy dx, equal, alright, 2 times up front, still 2 times, natural log of x minus 2, that will be 1 over, derivative of the outside is 1 over x minus 2, times derivative of the inside, the u prime is just 1, minus half times derivative of my natural log of a u is 1 over u, or 1 over whatever it is here, the x squared plus 1, times derivative of the inside, or u prime, which is 2x. Alright, let me simplify this right hand side real quick. 1 over y times y prime, and this term would just be 2 over x minus 2. Let me write this nicely. This is a y prime minus the bottom two, top two cancel out. That leaves me with the x on top. So that'll be x over x squared plus 1. Alright, so to get y prime by itself, or dy dx by itself, I will times both sides by y. So that'll be y prime equal to y times 2 over x minus 2 minus x over x squared plus 1. Alright, and this y, if you can recall, y is the same thing as this thing. So now I can substitute all these guys for this y right here. So that will be y prime equal to the original problem itself, x minus 2 squared over, I'm going to write the square root of x squared plus 1 as x squared plus 1 to the half power. Alright, times, I'm going to go ahead and subtract what's inside my parenthesis here. LCD is x minus 2, x squared plus 1, and the reason why I write x squared plus 1 as a half power, because I got another x squared plus 1 here. In a minute I'll actually put them together. Alright, so LCD is x minus 2 x squared plus 1. So my first denominator is missing x squared plus 1, so that'll be 2 times x squared plus 1 minus x times, second denominator is missing x minus 2, so negative x times x minus 2. Alright, so if I simplify the top, x squared, the x minus 2 squared over x squared plus 1 to the half power, times, this is 2x squared minus x squared, which will give me x squared. Alright. Negative x times negative 2, positive 2x. And 2 times positive 1, positive 2. Over down here, let's do the same thing. Alright, so I got x minus 2 squared on top. One of them can cancel with the x minus 2 in the bottom. So that leaves me with 1x minus 2 on the top, and times my x squared plus 2x plus 2. Alright, over. So the bottom x minus 2 is gone. So here I got x squared plus 1 to the half power, the other one to the first power. Alright, so use power rule here, I can add them up. Half plus 1, that will tell me this is going to be x squared plus 1 to the 3 half power. Okay, half plus 1 is 3 half. There you go. That's the answer. Okay, now I could have used, quotient rule for the right hand side, but I just want to show you another technique using logarithm, okay, to help us differentiate, okay, using implicit differentiation. Alrighty, thank you for watching this video.